Okay, I'm going to finish off here. We're gonna talk about the midterm and talk about what's going to be on it, how the test is going to go, and that sort of thing. So basically, the test is going to have some short answers. In other words, you're gonna put an answer. There's going to be a question. You're going to put an answer down, and some of that is going to include questions on the. Some of that's going to include drawing like a diagram, so that you'll have to understand that for example, today, that in order to calculate a watershed, what are the whole process that goes into calculating a watershed. So starting, like if I say, okay, I got a watershed and I've got an elevation data set, what are all the tools that I need to run to get to the watershed? So you need to be able to diagram that process out or describe it. And so those are the two types of questions. Now also another type of question, actually, so there's three types of questions. So the short answer questions, the modeling questions, and then finally there will be some questions where you'll get a small grid, kind of like what you did for this lab, and you'll have to produce the answer. Okay, and like they'll look like this. This was from today. I'll just create another sheet though. Okay, so they won't look like an Excel. Well, they kind of might look a little bit like an Excel spreadsheet, but I'm gonna make these look a little bit more like a raster. Okay, so and then I could even make all these guys be in the middle. Okay, 5, 3, 4. Let's just say we had 2 of them. So I might have a question like, what if we were to add those 2? That's a really easy one, but that could be an example of a question. If we were to add this raster to this raster, I should probably like color them like this. So if we were to add this raster to this raster, what would the result be? And you probably don't have to calculate the whole result. What would the result be? So it'd be 5 plus 2 would be the first one, and then 5 plus 4. So equivalent cells get added to each other. Right? So that's an easy example. Now, something that might be slightly more complex is that you might see something on the test where there's a conditional statement where I say, if the value in the raster is greater than 5, then I want the output raster, in this case, let's move and copy this. So here's my copy. So what if the output raster, I say something like, is the con of the input raster greater than 5. Now, if I just put that, the values will be either 0s or 1s, right? But if I did something like this and said, if the true raster is 0 and the false raster is 1, then it would be the same thing. Sorry. Okay, or if I said it's going to equal 105, then that would be a little bit more tricky, but you could still do it. So if this is true, it gets the first value. If it's false, it gets the second value. So how would this be coded? Is 5 greater than 5? No. So what's the false value? 5. Yep. And then we know 3 is not greater than 5, and so on. Okay, is 8 greater than 5? So the true value is 100. So it looks something like this. Now again, on the test, I rarely ask you to fill out the entire value. It's just once. Okay. But there's going to be some examples of these are all local operations where it's a one-to-one comparison. But there might be a question like this too. So here there might be a question like this where I ask you what the focal mean is, or what the neighborhood mean is for this cell. So how would I calculate the neighborhood mean for that cell? Neighborhood average. What's the neighborhood average? How would I do that? You don't have to actually calculate it. How would I calculate I'd also have to specify what the neighborhood is, right? Okay, let's say the neighborhood encompasses that entire window, that entire area. So this is the neighborhood.
Oh, then you add up all the squares and divide it by the number of squares? Put it in the center?
Yeah, so you add up all the squares. So it's 5 plus 5 plus 6 plus 3 plus 2 plus 7 plus 4 plus 1 plus 8.
Divided by 9.
Divided by 9. That's what that is. Now, I might say, I'm going to use mean. I might say the minimum or the average, something like that. Okay. If it's so average is the same as mean. Now, I will be fine if you have questions during the test. Like if you say, if you ask a question that, say I don't. Like I'm not going to redefine a term, but we're going to all take the test together. So if there's something that you need to ask about that, I can try to answer that. All right. Now, also zonal statistics. Okay. So what if instead of having the input and the output here, what if this was 1, 1, 1, 2, 2. 1, 2, 2. What's the zonal mean of the area that are ones? How do I calculate that? Well, what's the zonal sum? That'd be easier. The zonal sum of the ones. This is my zone table. I'll specify that. My zone raster. And then this is my value raster. So what is the zonal sum of the ones?
$22.
5 plus 5 plus 6 plus 7, is that 22?
23.
Okay, yeah. So if we did a zonal statistics as table with this, we should get something like this. 1, 2, sum is 23, and what's it for 1, 2? 2 plus 3, 5, plus 4 is 9, 10, 18, something like that. Okay. And then same thing with mean. How would I do that? We'll take this divided by 4 because there's 4 of these cells equals this divided by 5. So that's the zonal mean of those two zones. Okay. All right. So doing things like this, it'll all be simple calculations. Like I'm not asking you to recalculate slope. Remember I showed the formulas for slope and aspect. That's not going to be on the test. So they'll all be fairly simple formulas, and you're welcome to use a calculator or
Is it a written test or?
Yeah, it's written test. It's interesting because in my other class I taught last night, we're also doing a test next week, and they just ask, is the test going to be on Canvas? It's like, is that happening more often?
Oh, yeah.
Okay, so I don't know. Maybe I'll surprise everybody and it'll be on campus, but I don't know how to do that right now. So, so I'll try. Yeah, I've mostly written up both of the tests. I have the test. Okay, so let's go back to the review sheet here real quick. So here, this is from the first week of class, and specifically here we talked about different types of models. We talked about different ways to categorize models, because really we're modeling the world when we do spatial modeling. And so we had things like scale models. A scale model is just a miniature version. We had graphic, mathematical. So ArcGIS Model Builder, for example, is an example of a graphical model of a process. And a layer in ArcGIS is an example of a scale. It's digital, but it's still a scale model of some distribution in the landscape. So an elevation, one reason why it's called a DEM, stands for Digital Elevation Model. It's a scale model of the elevation and stored in digital format. Let's see, yeah, mathematical. I think today we had a mathematical model that described a process, and that was runoff. So that's an example of a mathematical model. We did graphical. Yeah. Let me see. I think that's all I really talked about on the test. We can model like a decision-making process. Suitability modeling helps us to do that. Okay. All right, then we talked about what a raster band is. We haven't actually used raster band data a lot, but really a raster band data is when a single file contains multiple rasters. We refer to those multiple rasters as bands. Okay, so a file usually is just one raster, like with elevation, but we have used some. So the imagery that we've used, there's really three different rasters. One that represents the red, the green, and the blue visible light. So there's three bands in those rasters. We could have a raster that represents something like sea surface temperature, and then we could have different bands that represent the sea surface temperature at different elevations, at different depths, I guess is a better way to say that. So a raster band is another way to say that is a multi-dimensional raster data set. A raster band is one dimension of a multi-dimensional raster data set. Specifically, each raster band takes up the same spatial location too, right? All right. So what is resolution? Well, spatial resolution is just another word for cell size. Spatial resolution and cell size are interchangeable words that have to do with how large a particular cell, how much area a particular cell represents on the ground. And almost always we express cell size as a single dimension, but that's actually not. We could have a raster where we have rows. The X cell size is different than the Y cell size. But usually we just say it's 10 meters cell size. That means they're square. But it is possible to have a raster that has rectangular cells, is what I'm trying to get at there. But we usually don't. We usually don't express that, and there's nothing about that on the test. So I don't know why I brought that up. So cell size is usually a single number, but my point is that it represents it's a linear unit, but it represents the dimension in both directions if only one's given. All right. It's not the area. It's the linear size of one side of the cell. All right. I did start recording again, right? What's that? I'm just making sure I did. Okay. So how are coordinates stored in the raster data format? This is something that's on the test, and it's also important that you understand this. So with a raster data model, you actually saw that this week more strongly than you did before. So we created this raster cell, and all we had, this raster data set, and the only thing that we needed to do to specify where it was spatially is to specify the X and the Y corner, and then the cell size. So in the raster data format, in the raster data model, which there's lots of raster formats, but in the raster data model, the only coordinate that's stored is actually the corner, and then the cell size is stored. The cell size is necessary. So it's the coordinates are all derived based on the corner of the cell. So we're not storing, like with a vector, you're storing a coordinate for every vertice. Points, lines, and polygons. Every vertice needs a coordinate point stored. With raster, we're really only storing the corner. And then we figure out where we are implicitly from knowing the cell size. So if we're in the third row in the fourth column, then in this case, we're 300 meters over and 200 meters, did I say 3 and 4? 400 meters down. We can figure out where we are. So the GIS figures all that stuff out for us. We don't have to, when we click on a point and we get an XY coordinate, we don't have to figure that out ourselves, but the GIS has figured that out for us. It didn't store any information about where things are. And that's why it's even more important when we do raster processing that our data is lined up correctly. But it does make it easier to line it up correctly, because if the corner is off, all we have to do is correct that one single coordinate. It's actually the reason that raster processing is oftentimes faster, because we're not dealing with a ton of coordinates. We're just dealing with a bunch of values. Okay. All right. All right, so that was how are coordinates stored in a raster? Yeah, well, just the corner and the cell size is all that's necessary. So basically, the coordinates are all stored implicitly from the corner. Okay, capability, suitability, modeling, terms and concepts. You should go back and review those. What's a constraint? What's a factor? And so on. Okay. All right. So this concept of map algebra, that's kind of what I was talking about. You should know, that's what I was talking about when I was doing these. You should know how the numbers actually change, but they're all pretty basic examples. But I said there's no slope or anything, but there are things like flow direction, and even though I didn't do examples of those, there's flow direction and there's Euclidean distance on the test too. So like, in other words, if I said, this is the cell I'm concerned about, and we're going to do Euclidean distance, what's the distance to, I won't say every other cell, but what's the distance to this cell? What's the Euclidean distance from the center of that cell to the center of that cell? What's that? That's exactly right. So the cells, let's say the cell size is 100. What's the cell? That's close. The shortcut is that it's 100 times the square root of 10, square root of 2. Okay, but if you wanted to figure out that distance, it would be this is 100, that's 100, and so it would be 100 times 100 plus 100 times 100. And we add those two together. That's why I said plus. And then take the square root of that value, and you get that. Okay. But the shortcut for a diagonal is just the cell size times the square root of 2, because it would work out to do that. But that only works if they're square, which they are usually square. The reason that that works is that you know, if A and A are the same, A plus A is the same as 2A, right? I just want 2 times A, right? That's the same thing. And so so that's where you get the square root. So you're going to get the square root of 2 times A is going to be this, because you're saying that C squared is equal to this whole thing squared. So the square root of 2 times A. That's how the math works out. Okay. All right, but yeah. I guess another. So you should know that. Like, what if I said this? What's the distance to there? That one is a little bit different, because that's not just the square root of 2 times the cell size, right? That's 200. So say 200 times 200. What? So equals. So that's the distance from there to there. Okay. All right. And the slides for that lecture did have an example on that. So no slope, no aspect calculations, no hillshade or visibility, but there were all the ones that I've gone over so far. Those are on the test. Okay. Okay, so yeah, that's what this is. Now we kind of breezed through this in the lecture, and there's not actually a whole lot of questions on these, but go back and look at the the Boolean and logical. Like if I had a question where I said, instead of saying are they equal, I've said not 5. So if I said that this were not 5, then if it's true, it's going to equal 1. If it's false, it's going to equal 0. It's another way of doing a conditional. All right. But conditional is on there for sure. These aren't. We kind of breezed through those on the lecture, but conditional is on there. You should be able to recognize the difference between a local, focal, and zonal operation. Okay. So local operations operate on a single cell at a time. Now that single cell, that's a single location. So if I add one raster to another, I'm looking through space. I'm looking at a single space in time, or single space per raster. So I can add 2 rasters together. I can even add 5 rasters together, or 6, using. There's that local. In ArcGIS, I think we used it once. Local. Oh, it's just called cell statistics. But that cell statistics is an example of a of a local operation that uses multiple rasters, but it's still just looking at cell by cell by cell. And then focal is looking at a neighborhood. So I go through. The concept of a moving window. Remember we talked about that in class. So a moving window, and there's a focus. So it's focal or neighborhood, and then finally we have zonal. Zonal is any operation where you're asking to summarize an area. Okay? It could be literally the sum, or it could be the mean of an area. It's a statistic about an area. Focal means that you go cell by cell and calculate a statistic about the neighborhood surrounding that cell. You can define neighborhood differently. Local means you go cell by cell and you're only examining that cell or other cells at that same exact location. You're not considering the neighboring values. So slope is a focal operation. Add, subtract, multiply, and divide. Any of these, those are all local operations. Anytime where I want to ask a question, what's the average elevation of the city of Hattiesburg? I would find that out doing a zonal operation. If I had the elevation of Hattiesburg, a digital elevation model of Hattiesburg, I could figure out the average elevation of the city of Hattiesburg with another raster that represented the polygon, the area that was Hattiesburg. All right, you do have to understand what slope, aspect, hillshade, and visibility do. In other words, what do they take as inputs? In each case, it's an elevation model. And what do you get as an output? And be able to understand what that output actually means. Now, some of these require a few other values. And I'm not talking about slope says you get percent or degrees. Okay, percent or degrees. That's neat that you can do that, but you could convert that later. Okay, if it always only did degrees, then you could convert it to percent. It's just a conversion factor. Okay, what I'm more interested in is that some of these actually require other inputs. So hillshade requires the solar position. Okay. Visibility requires the position of the observer. But slope and aspect, they only require really the only input is the elevation. Okay. All right, distance. So you should be able to understand both cost and Euclidean distance, although you're not gonna calculate cost distance, but you should understand what's going on there, and that you should be able to actually diagram a cost distance problem. So with cost distance, it requires one of the inputs to creating cost distance is that there needs to be a source. Like you are that you can only calculate cost distance if you know a source and what else? The cost raster. So the cost raster and the source go together to create a cost distance, and the output, every cell represents the distance back to that source through the cost raster. What does cost represent? Well, cost can be anything. It could be dollars, it could be time. It's an impedance factor. It's the cost for traveling through that cell. So you should understand that. Okay. And then what we did today, the water modeling concepts and the workflow. I think that sometimes it's helpful to go back and look at the ARCGIS help for the operation. So for the operations that I have here, kind of review what are the inputs and what are the outputs that you would expect to get, and study that information. So for each of these, not local focal, but for each of these, and for cost distance, and for the water modeling concepts, go back and study that. So you're also going to have to create at least one diagram of the workflow for a given problem. So it could be cost surface, it could be water modeling, it could be capability suitability modeling too. Okay, I didn't put that on there, but that was the other concept. So we started out talking about, in general, different types of raster GIS operations: local, focal, zonal, and then the three concepts that were taught this half of the course were capability suitability modeling, cost distance modeling, and distance, and then water modeling. So if you understand the flow of those three, I think you should do well on the test. Let me look at Yep. Oh, two more modeling terms that I left off. So mathematical models, because I talked about scale, I talked about mathematical, I talked about graphical, but mathematical models can be divided up, and so far most of the mathematical models we've run would fall under what we call deterministic. In other words, there's only one result for given inputs. But if the particular mathematical problem is so complex, like it represents something in reality, and we try to model the uncertainty that's there, we could call that a stochastic model. In other words, every time we run the model, it might be slightly different because we have a stochastic or a probabilistic factor in there. So we could have made, like, let's say, it's interesting that worked, running that process. Oh, yeah, I was trying to find ArcGIS Pro. So instead of using the formula for coming up with, by the way, I did update this with the thing Avery pointed out, with 1 minus. I uploaded that to the canvas. So what we could say is that we know that the water goes into the landscape, but we're not for sure. There's other things that we're not so certain about, and if instead of saying that it was this formula, I forgot what the formula. Oh, it was 1 over the impervious value divided by 100. We could say that instead of just the impervious value times 100, we could say times some random number between 0 and 10, and then every time we ran, it would be slightly different. That would be a way to introduce a stochastic element to the question. It's really something that we cover a little bit more in 517, that course, than we cover here. We talk about some stochastic models in that course. So basically, they're models that the outcome is based on some probability rather than being a single answer for every set of inputs. Okay, so that was from the first or second week of class. Okay. If we're going to take, if we have costs from a lot of different data sets and we're going to combine them, we could just add them all up, right? Like we could combine, we would do that example with the railroad model. We could add up all our costs, but it's important that our costs be in the same units if we do that. So that's something to remember. All right, I think I've gone over the test and given you some stuff to study. Does anybody have any questions? All right, so next week we'll have the test, and we'll just have the whole time for the test. So you'll have, let's just say all the way till like 4 o'clock, since I said the whole time once and I messed up, and people were like, "What does that mean, the whole time?" Of course, I can stay longer, so I'm not super concerned about the time limit here. But I didn't write the test to last 4 hours, so I think most of the time you should be able to complete it. But I'm happy to stay a little bit longer to help to have anybody finish up. Any other questions?
Dr. Raver, so are we gonna have to print it out and scan it back to you?
That's a good question. I'm going to try to do the. I think I'm going to try to do the Canvas thing. So
Okay.
I'll try to put it on Canvas, and that way. But the problem with that is that I have you draw some diagrams. I don't know if I can do that. So if that doesn't happen, then yes, we can do that. And I actually have to come to Stennis, so I may come to Stennis for the test, and yeah. So look for how I'm going to handle Stennis soon, but I do have to come to Stennis to renew my my pass, so I could have somebody proctor here, and Joseph will proctor here, and then I could have somebody proctor in Hattiesburg. So anyway, we'll figure that out.
Okay, thanks.
So yeah, it'll either be like what you said, or okay. Any other questions? I got a meeting with a student at 4, so that's 9 minutes. But that probably won't take very long. But if anybody has any questions as they work through the lab, let me know. I usually I'm usually in the field or do field work on Mondays. I will be on campus on Monday, so on Hattiesburg campus. So if anybody has questions up there and they get frustrated today, I'll be there on Monday. I'll be there on Tuesday and Wednesday and Thursday as well. But if you have questions, for those of you here, we can get on the Skype for Business. Communicates directly. We can even screen share, and I can answer questions as well. So, all right. So, I'm gonna stop this recording.